Okay, and finally in our kinetics unit, a catalyst. So what is a catalyst? Well, let's see. A catalyst is a substance that increases the rate of reaction. But how does it do that? It creates an alternate pathway that has a lower activation energy. So if you remember from before, a catalyst does not change the equilibrium. What it does is it speeds up the forward and speeds up the reverse reaction. So we get to equilibrium faster, but it doesn't mess with the equilibrium. But in this lesson, what we're talking about is how a catalyst literally just creates an alternate pathway. It's like, hey, you don't have to go here. You can just go like this. So it's like finding the shortcut. Okay, so a catalyst is like finding the shortcut. So you don't have to take the long way. You can go the short way. So how do you represent that? Okay, so like this. Here is the alternate pathway. So normally we would go from reactants all the way up with our activation energy to the top of the activated complex and then back down to our products. Okay? Now, when we have a catalyst, we still start in exactly the same place with the reactants, but we need less energy. So we have a lower activated complex. So see, our activated complex is lower, and then we're going to end up in the same place with the products. Okay, so we don't change the start and we don't change the end. We just make it a little bit of a shortcut, but the shape has to be the same. Okay, so we start with reactants, go up, but not as high, and come back to the products. So here we start with reactants, go up, but not as high, and then back to the products. So there is the pathway for a catalyst. A catalyst doesn't get used up in the reaction. It's just like a helper. Okay, so it helps the reactants combine to form the product, also helps the reverse reaction, but it doesn't get used up. So remember, again, a catalyst does not mess with equilibrium. It just gets to equilibrium faster because the catalyst increases forward and increases reverse reaction. So here's another visual. So we have our reactants. We start in the same place. Okay, with no catalyst, we got to push all the way this way, long way, long way. Okay, but if we have a catalyst, then we need less activation energy. It's a little easier. It's a shortcut. So in biology, we call those catalysts enzymes. Okay, so an enzyme is a catalyst. All right, so here again, reactants, products. Whether we're talking with or without a catalyst, those locations don't change. Without a catalyst, big activation energy, tall activated complex. With a catalyst, much less activation energy, small activated complex. So, common question, add a line for the catalyst. So again, remember, we start the same for reactants and products. We follow the same shape, it just is going to be underneath, so lower. So like this. Follows the same shape, starts at reactants, ends at products, but it's lower. So again, on this one, start with reactants, end with products, follow the same shape, but don't go as high. Okay, so easy peasy, draw a line to show a catalyst. All right, so the effect of a catalyst on a chemical reaction is to provide a new reaction pathway that results in a different what? Activation energy. Remember, the start, reactants, the end, the products, the same. So if we start the same and end the same, the little sandwich for the heated reaction in the middle is also the same. Adding a catalyst can speed up a reaction by providing an alternate reaction pathway that has a lower activation energy or a lower activated complex. What occurs when a catalyst is added? So do we have the same pathway? Negative. So this is wrong. This is wrong. Alternate pathway, does it have a higher or a lower activation energy? Lower, right? All right, so here's a potential energy diagram. Which intervals are affected by the catalyst? Well, does the catalyst change where the reactants are? Nope. Does the catalyst change where the products are? Nope. So Did it change number 2? No, that's wrong. That's wrong. Okay. Does it change number 4? Well, if I don't change where the reactants are and I don't change where the products are, then the little sandwich, that heat of reaction in between, that doesn't get changed either. So that doesn't get changed. So it appears that 1 and 3 would change. Let's double check. So 1 is the activation energy, right? Going from the reactants to the tip top. And 3 is the activated complex. So if I change the color, if I added a catalyst, start the same, follow the same shape, just go lower, end the same. Oh, yes, 1 and 3 would be different. All right, which potential energy diagram represents a change in potential energy that occurs when a catalyst is added? And so look, we have solid line with no catalyst, dotted line with a catalyst. So, well, you should remember, same shape. So if it follows the same shape, then that means this is wrong. That is just a complete straight line, okay? So it follows a straight line with some requirements. We need to start at the same place and end at the same place. Our line just should follow the same shape, but be lower. So does this start at the same place? Nope. Does this start and end at the same place? Nope. So that means that has to be my right answer. And there you go. That's catalysts. I hope you learned something new today.